So we continue our study of the Lebesgue measure, and in this lecture we will look at three main properties of the Lebesgue measure on Lebesgue measurable sets. The first one is called upward and downward monotone convergence theorems, and the second one is the dominated convergence theorem, and the third one is called inner regularity with respect to compact sets. So all of these, so let me put this as a remark that all these properties, all the above properties are essentially consequences of the countable additivity of the Lebesgue measure. Countable additivity property, additivity property of the Lebesgue measure. So let me state these properties as lemmas. So the first one, so let me call it lemma 1 A. This is the upward monotone convergence theorem. And this states that if n equal to 1 to infinity is a collection of Lebesgue measurable sets in Rd such that we have a nested sequence of non-decreasing sets. E1 is a subset of E2, is a subset of E3, and so on, and all of these are subset of Rd. So this is a non-decreasing sequence of Lebesgue measurable sets. Then the measure of the union n equal to 1 to infinity En, which is again Lebesgue measurable. So the measure of the countable union of all these Ens is equal to the limit as n goes to infinity of the sequence of measures M En. So this is the upward monotone convergence theorem. This is upward monotone means that we are going higher and higher in the nested sequence of sets, and monotonicity property of the Lebesgue measure gives the name monotone convergence theorem. So this is the upward monotone convergence theorem. The second one is the downward monotone convergence theorem. So this states that if again En is a collection of non-increasing, so this is the reverse way, sequence of Lebesgue measurable sets, such that at least one of the Ens has finite measure. So in symbols we have E1 is a superset of E2, is a superset of E3, and so on, and all of these are subsets of Rd, and Men is finite for at least one n in the natural numbers. So then we have that the measure of the intersection now of all these Ens, n equal to 1 to infinity, is equal to the limit n tends to infinity of the sequence MEN. So notice that in the part A there is no assumption for finiteness of measure of any of the ENs, but in the second one we do need that MEN is finite for at least one of the ENs. So let's see the proof of this lemma. So for part A we have that the union of all these ANs, EN, this can be written as, so let me denote this by E, and this can be written as a disjoint union of sets n equal to 1 to infinity En minus union k equal to 1 to n minus 1 Ek. So these are called lacunae for the sets En, for the sets En, and this makes each of this lacuna disjoint from any other lacuna. So, and this also gives you an increasing family of sets. So let me write, if En prime is equal to this En minus this lacuna k equal to 1 to n minus 1 Ek, then E prime n intersection E prime m, this is equal to the empty set if and only if n equal to m. So this is the collection of En primes is pairwise disjoint. It's a disjoint collection of sets, and each En prime is Lebesgue measurable, because the finite union of EKs is measurable, the complement is measurable, and then again there is an intersection with the Lebesgue measurable set En. This is also measurable. So for each En prime is Lebesgue measurable. So therefore we have, therefore the measure of E is equal to the sum n equal to 1 to infinity MEN prime, because since E is a disjoint union of all these Lebesgue measurable sets, we have from countable additivity property, countable additivity property, we have that the measure of E is just the sum. So this is for any collection of countable collection of Lebesgue measurable sets En, but in our case we have a non-decreasing sequence. E1 is a subset of E2 is a subset of E3 and so on. So the union n of k equal to 1 to n minus 1 Ek is nothing but En minus 1. So in our case this lacuna En minus k equal to 1 to n minus 1 Ek, this is nothing but En minus 1. So once we have this formula, we can rewrite it. So now for our case, the union of all these ENs, when you have a non-decreasing sequence, this is equal to the sum of the measures MEN minus En minus 1, n equal to 1 to infinity. And this is by definition the limit of all these partial sums n equal to 1 to k equal to 1 to n m e k minus e k minus 1. This is by definition of the infinite sum. Here we let E0 to be the empty set, because if k equal to 1 we will get E0, but our sequence of sets starts from E1, but we can without loss of generality write E0 to be the empty set, and so now this limit formula makes sense. So now we look at these partial sums, k equal to 1 to n m e k minus e k minus 1, but because each of these, for each k, this is a collection of disjoint sets, the lacunae are disjoint, so this is nothing but the union k equal to 1 to n e k minus e k minus 1, but since e k minus 1 is a subset of e k, this implies that the union k equal to 1 to n e k minus 1 is nothing but E n, because so this is something like this as a Venn diagram. You have E1, then you have E2, then you have E3 and so on, E3, and so if you take, for example, here if you take union k equal to 1 to 3 e k minus e k minus 1, so the first part is nothing but, for k equal to 1, this is nothing but whole of E1, then you will get this part in red, E2 minus E1, and then you will get E3 minus E1. So in total you will get nothing but the last term of the series, which is nothing but E3. And similarly you can check this with set arithmetic again, that indeed the union of these lacunae will give you En. So therefore on the right hand side we get MEN, and so we get our required result, that this union has measure given by the limit of MEN. Notice that we did not assume any finiteness of the measures, but because we are not cancelling anything from both sides of the equation, so we can, all the arguments that we give works whether each of these measures are finite or infinite. Now let's see part B. Here we have a non-increasing sequence of nested Lebesgue measurable sets E3 and so on, and such that at least one of the ENs has finite measure. So note that without loss of generality we may assume that the measure of E1 itself is finite. Otherwise there can be a renumbering of the sequence and the limit remains unchanged. So we can assume that the first one, E1, has finite measure. So now let again GK be the set EK minus EK plus 1 here, because it's an increasing it's a decreasing or rather non-increasing family of sets. So earlier we took ek minus ek minus 1, but here we have to take k plus 1. So this is a Lebesgue measurable set, and again this family of gk's is pairwise disjoint, meaning that gk and gk prime have empty intersection if and only if k is not equal to k prime. So you can check this using again set arithmetic that indeed this is the case. So now I make a claim, so let me write it as a claim. I claim that E1 can be written as the union k equal to 1 to infinity gk union with the intersection of n equal to 1 to infinity en. So let me write this as E. So this is E union k equal to 1 to infinity gk. So now note that E and this union k equal to 1 to infinity gk are also disjoint. Okay, so E1 can be written as a disjoint union of a countable disjoint union of sets E and the gk's, and so if we assume that the claim is true, assuming that the claim is true, then we have that the measure of E1 is equal to measure of E plus the sum k equal to 1 to infinity measure of gk, and gk was this set ek minus ek plus 1. So if you write this as measure of E plus the limit as k tends to infinity, or rather n tends to infinity, k equal to 1 to n m gk. So this is by definition of the infinite sum again. So now we are going to see what these partial sums exactly are. So let's see. So this sum k equal to 1 to n m gk, this is nothing but the first term is m g1, which is m e1 minus e2 plus m e2 minus e3 and so on. So the last term is m e n minus e n plus 1. So because all of these are finite, we can write this as m e1 minus m e2 plus m e2 minus m e3 and so on, and the last term is m e n minus m e n plus 1. So I'll put this as a remark that this above equality holds since m e k is finite for all k greater than or equal to 1. So now notice that we have many cancellations. So here we have m e2 minus m e2 and plus m e2 cancel out. Similarly minus me3 will cancel out with the next term, which will contain plus me3 and so on, and men will also cancel out with the last term, because the n minus 1 term is men minus 1 minus men. So this term and this term will cancel out, but we will be left with men plus 1 and me1. So this is nothing but me1 minus men plus 1. So therefore we have that measure of E1 is equal to measure of E plus measure of E1 minus measure of the limit n goes to infinity men plus 1. So since again me1 is finite, this implies that we can cancel out me1 on both sides, and so me is equal to the limit n goes to infinity men plus 1, which is the same as the limit n goes to infinity men. So we are done, except that we have to prove the claim. So now let's prove the claim, proof for the claim, which stated that E1 is the union of the intersection of all ENs and the union of all the with the union of all the GKs, k equal to 1 to infinity GK. So this is nothing but, so let me take this right hand side, n equal to 1 to infinity union with the k equal to 1 to infinity, and GK is EK minus EK plus 1, and so this is equal to the intersection n equal to 1 to infinity En union with the union k equal to 1 to infinity EK intersection EK plus 1 complement. And now we can distribute this set and take this inside the big union. So this is k equal to 1 to infinity intersection n equal to 1 to infinity En and then you have a union with EK intersection EK plus 1 complement, and then again we can distribute this inside the intersection. So you will get EK union of the intersection n equal to 1 to infinity En, and then there is a there is an intersection with the EK plus 1 complement union with the intersection n equal to 1 to infinity En. Now notice that the first one is just EK, because this intersection is contained inside EK for all k, and so we have k equal to 1 to infinity EK intersection with this second term, which is EK plus 1 union with the intersection of all ENs. Now we can again distribute this EK inside, so we will get, so here we have k equal to 1 to infinity EK intersection EK plus 1 complement, which is nothing but EK minus EK plus 1, and then you have a union with EK and then the intersection with the all the intersections intersection of all ENs, but this is again EK and this is a subset of EK, so the union is again EK. So therefore you get k equal to 1 to infinity EK, but since it is a non-increasing sequence, this is nothing but E1. since ek is a subset of E1 for all k greater than or equal to 2. So therefore we have proved our claim, and so this proves the downward monotone convergence theorem. One remark about the downward monotone convergence theorem is that we cannot remove the condition, remove the assumption that at least one MEN is finite. So as this example shows, so you can take En to be the set n to plus infinity, so it's an unbounded set. So it's a Lebesgue measurable set and it has measure plus infinity. In fact this is an elementary set, so the measure is plus infinity for all n greater than or equal to 1. So the intersection of all the ENs is empty, so the measure of the intersection is 0. So this is not equal to the limit of the measures MEN. So as this example shows that we cannot remove the assumption that at least one of them has finite measure.